Hi, welcome to this lesson on trigonometry, trigonometric functions, part 1. Let's have a look at question 2. The graph of f of x equals cos 2x is drawn for the interval between negative 270 degrees and 90 degrees. The graph of g of x is 2 sine x minus 1 for the same interval. We want to draw that graph on the same system of axes and clearly label all intercepts and turning points. Okay. So this graph here in red, that is the graph f, which is cos 2x. So we want to draw this graph here now, 2 sine x minus 1. So what I'm going to do is bring up the calculator, and we're going to use the table function again. So we go mode, table. So 2 sine alpha x, close brackets, minus 1. Okay, make sure you write it exactly the way you see it. Okay, we don't have a second function we're drawing from negative 270 and it goes all the way up to 90 degrees. Okay, end at 90. And the steps we're going to take, okay, I always go default as 30 degrees. I mean, the spacing is given on the graph is an indicator of what you can do, but I like to put as much information as possible to get a good, accurate sketch as possible. Okay, so negative 270 degrees, it is the value 1. Okay, so first of all, where is 1 here on the y-axis? Well, we know this is cos 2x. When we put 0 degrees here, we're going to have cos of 0, which is 1. 0 degrees 1. So this is y equals 1 here. Alright, so at negative 270 degrees, it was also 1. It's an endpoint, so I think it's important to label that. Negative 240 degrees is 0.73, which is just below 1. Okay, so let me go on here and just split these values evenly. Okay, between negative 180 and 270, that is 90 degrees, so 45 degrees either way. All right, and that value is going to be negative 225 degrees, I believe. Same thing should happen here. Negative 135 is halfway between those. And then negative 45 degrees, 45 degrees, and 90 degrees there. Okay, these are just the values for that cos 2x graph. Okay, so I think maybe let's stick with 45 degrees so we can see it a bit easier. So we'll go there, there, same things again, but now the step is 45 degrees. Okay, so at negative 270 degrees, it's 1. At negative 225 degrees, it's 0.41, so just under halfway. Okay. At negative 180 degrees, it's exactly negative 1, which is going to be over here. Because we know cos 2x, that 2 there just means the period, right? The new period is 360 divided by 2, which is 180 degrees. So you can see every 180 degrees, the cos x, or the cos wave does a full wave here, the cos 2x. Okay, so that means the range is still going to be between negative 1 and 1. So at negative 180 degrees, it was negative 1, and that's a turning point, right? Okay, then negative 135 degrees is negative 2.414. Okay, so there's negative 3, so it's about almost halfway there. So I would say over here, right? That's negative 135 degrees. At negative 90 degrees, it's negative 3, which is over here. And that would be a minimum, right? Because if we analyze 2 sine x minus 1, what are the parameters that are affecting it here? There's an a value and a q value. The a value means we're stretching the parent graph sine x by a factor of 2 vertically, and the negative 1 means we shift the entire graph down by 1 unit. Okay, so the range gets affected appropriately. So the normal sine x graph was between negative 1 and positive 1 for the range. So if I multiply both sides by 2, that becomes this inequality here. And then if I subtract 1 on both sides, it becomes negative 3 between and greater than 1. So there's your new range, from negative 3 to positive 1. So because I have a negative 3 value here, that means that's going to be my minimum turning point. At negative 45 degrees, we get the same symmetry going on here, so negative 2.414. At 0 degrees, it is negative 1, and that's a y-intercept. At 45 degrees, it is just under half. Okay, and that's an endpoint, so I would put it there. 45 degrees, 0.41 to 2 decimal places. Okay, so if I go ahead and sketch this graph now, it's going to look something like this. Okay, so we've got the turning points, but we don't have the intercepts. So first of all, there's an x-intercept here and an x-intercept here that we need to find. Once we've got that, then we've got all the information we need. So how would I solve for that? Okay, so what I'm going to do is I'm going to solve g of x equals 0. So that means we're solving 2 sine x minus 1 equals 0 to get the x-intercepts. Okay, if I get sine x by itself, move over the 1, then divide by 2, so I get sine x equals a half. Okay, but that is a very, very special angle, right? Sine of what gives you half is 30 degrees. So here, 30 degrees, 0 is the one intercept. And where else will you get? So if I did a general solution to this, I know the reference angle is 30 degrees, and sine is positive in the first and the second quadrants. So the first quadrant solution would look like this: 30 degrees plus k times 360. Or the second solution would be 180 minus the reference of 30, so 150 degrees plus k times 360, where k is an integer. Okay, so let's go back to mode 1 for computation. If I look at the first one, 30 degrees, if I subtract 360, negative 330, that's way outside this range here. So that's not going to be it. So I'll try the other one, 150 minus 360. That's going to give me negative 210 degrees, which is within this range here. Okay, so I used the second general solution set when k was negative 1 to find that solution within this given restricted domain. Okay, and that is all the valid information you'll need to sketch this graph. Now let A be a point of intersection on the graphs of f and g. Show that the x-coordinate of A satisfies this given equation. So let's go back up here and see when does the graphs f and g intersect. Well, here's a point of intersection right here, and here's another point of intersection right here. We want to show that, so this could either be A or this could either be A. We weren't exactly told, but we want to just show that the x-coordinate of A satisfies this equation. So we are solving f of x equals g of x. That is points of intersection. So this is true if and only if f of x was cos 2x and g of x 2 sine x minus 1. Okay, so there's a few ways we can try and solve this equation, but I want to try to get everything in terms of sine because this gives me the clue that I need something with sine x. Okay, so cos 2x, that's a double angle identity. And I think what I'm going to do to try and keep it in terms of sines only, I'm going to rewrite it as 1 minus 2 sine squared x, one of the three variations of its double angle. Okay, now I can solve this equation. So I bring over the negative 2 sine squared x to the right. I bring over this positive 1 to the right, so it becomes negative. So the 2 sine x is still there, minus 2 equals 0. And if I divide both sides by 2, I get sine squared x plus sine x minus 1 equals 0. Now this looks like an equation that we are familiar solving. Okay, so if I do some k substitution, so our algebraic toolkit comes out. If we let k equal sine x, then this thing becomes sine squared x means sine of x all squared, so k squared, plus k minus 1 equals 0. Now this is a quadratic equation in the general form. So look how we suddenly went from trig functions to algebra now. Okay, so now how do I solve for k? Yeah, I can use the quadratic formula. So k equals negative b plus minus the square root of the discriminant term, b squared minus 4ac, all over 2a. So my a coefficient here is 1, my b coefficient is 1, and my c coefficient is negative 1. So it becomes negative 1 plus minus square root 1 squared minus 4 times 1 times negative 1, all over 2 times 1. So it's negative 1 plus minus. Inside the surd, we have 1 minus 4 times 1 times negative 1. So the negative 4 times negative 1 is positive 4, plus the 1 squared, so that's 5, all over 2. So what have we got here? K, which is sine x, so sine x equals negative 1 plus root 5 over 2, or sine x, the k value, is negative 1 minus root 5 over 2. Now notice this one only has plus. So what happened to this solution here? Well, first of all, let's recall the basic properties of a sine graph. The range goes between 1 and minus 1. That's a very underappreciated and extremely important property of the sine graph. So if I take out my calculator and I work out negative 1 minus root 5 and then divide by 2, I get negative 1.61. Now that value is somewhere down here, negative 1.61. Your sine graph does not go there at all. So this one here has no real solutions. So we can discard that one, and the only one that's left over is this one, and we can check that that works because negative 1 plus root 5 and then divided by 2 gives you 0.61, which is somewhere here. So that makes sense. It does have multiple solutions. Okay, and then lastly, calculate the coordinates of the points of intersection of those two graphs. Okay, so we know that f of x is equal to g of x, the points of intersection, if and only if we would just show now that sine x is negative 1 plus root 5 over 2. So we can solve this trigonometric equation. Right, so we know this was a positive number. It was like 0.6 something, right? 0.618. Okay, so cast diagram. Where is sine positive in the first and the second quadrants? So the reference angle is going to be sine inverse of this number. So shift sine inverse of the answer. 38.17 degrees. Okay, so that's that acute angle here as your reference angle. So now the quadrant 1 solution is x equals 38.17 degrees plus k times 360 for the period of sine. And the quadrant 2 solution is x equals 180 minus that reference value. So let's go 180 minus that answer, 141.83 plus k times 360 degrees. Okay, so let's apply it to this restricted domain here. So when k is 0 for the first quadrant, x is 38.17 degrees, which is valid. K greater than or equals to 1. So because it's k times 360, the values are going to be much bigger than 90. Okay, they'll be even bigger than 360. So no applicable solutions. What about k is negative 1? Let's try that and see if we get anything. So what I'm going to do is, let's see, minus 180. I'm just trying to get back to that reference value, 38. Okay, so there's it over there. So now I'm going to subtract 1 amounts of 360, and I get negative 321. Way outside that domain. So anything less than equals to negative 1, not applicable. So there's the only solution there in that given restricted domain. When k equals 0, you're going to get 141.83 degrees. That's not applicable. K greater than or equals to 1, definitely no applicable solutions, much bigger than 90. What about k equals negative 1? Let's try it over here now. So just trying to get back to that value. So that's going to be minus 180 times negative 1 there. Okay, so I'm just getting back to that value there, 141.83 degrees. Now if I subtract 1 amounts of 360, negative 218.17. That x value is definitely within that restricted domain. And anything less than negative 1, so negative 2 onwards, won't work. So let's check if this makes sense. 38.17 degrees. There's the point of intersection. That looks about right. It's bigger than 30 but less than 45. So that point of intersection is 38.17 degrees. And did they want the full points or just the x values? They want the full coordinates, so we need to find the y value, so we'll substitute that in. And the other one was negative 218.17, which is over here. That also looks like it makes sense. Okay, because it's less than negative 210 but greater than negative 225. Okay, so we just need to put these values into any one of the functions and we'll get the answer. Okay, so I'll just use f of x equals cos 2x. So cos 2 times negative 218.17 degrees. You can also use the exact values, it's fine. So you get 0.24 to 2 decimal places. Okay, that's the one coordinate of intersection. And the other one was 38.17 degrees. All right, so plug that in, 0.24 as well. Okay, so that also worked out nicely. Okay, so those are the 2 points of intersection of those two graphs in that given interval. Awesome. I'll see you in the next one.